So now the last thing we want to look at in regards to vectors is what happens if we have a vector valued function. So we not only just have the vector itself, but now the components of the vector won't just be numbers, but they'll be functions themselves. So let's just start with the definition of what exactly this is. Okay, so a vector, so we call it a vector valued function. Okay. So this is a function in the normal sense that we always use the word function of the form. We typically like to use R for this. So R of t, again, this would be bolded if you're typing it, is equal to f of t times I hat plus g of t times j hat. So remember, this is the way we can represent vectors, which would be similar to this component form where we have f of t comma g of t. Okay, so two different ways to write the same thing. And then maybe you have it a three-dimensional case, then you would add on like an h of t times k hat, etc. Right? So it'll extend naturally to the third dimension pretty easily. So let's just look at an example right away so we can kind of get a feel for what exactly this is. So let's say that we have the function r of t is equal to t squared minus 3t times I hat plus 4t plus 1 times j hat. Or again, you might write it like this. And I won't write it both ways every single time, just to kind of get a feel for the different ways you might see this. And in fact, I think with these kind of functions, it's also common just to see these as column vectors. And we use these very commonly in statistics also, so I think it's good to get used to the column vector notation anyway. But this, if you've ever looked at a specific type of functions called parametric functions, which are sometimes covered in different calculus classes, we skipped it when going through Math Tools 2. But this is basically the same kind of idea that we see with parametric functions. So we usually use t as the variable here because t represents time, and these are typically used in applications where your variable might be the time variable, but not always, of course. So in general, if we want to evaluate these, it's pretty straightforward. We just evaluate the f part and the g part separately. So for example, if we wanted to evaluate r of 0, we would get 0 squared minus 3 times 0 for the top one, and then 4 times 0 plus 1 for the bottom one. So we'd get 0, 1. And then if we wanted to put these on the graph, this kind of gives us an output. So this is a point on the graph, 0, 1. So I guess I can go ahead and graph these as we go. Okay. So 0, 1 is 1 point on our graph. R1. So this would be equal to 1 squared minus 3 times 1, and then 4 times 1 plus 1. Again, I'm using the column vector notation, but you'll see this in all of these different notations. Most like beginning calculus books, I think, will probably stick with the unit vector notation. Okay. So anyway, so 1 minus 3 is negative 2. 4 plus 1 is 5, so we have negative 2, 5. So this would be like the coordinate, the point negative 2, 5. I just went the wrong way. So this way, negative 2, 5. Okay. So like typically to graph these, we just take the first one to be the x and the second one to be the y, because that's the usual order of points that we have here, right? When we look at the component form here. Now if we do r of, some of these are going to get off the graph, so let's just do like r of -1. Do component form this time. So we have -1 squared plus 3, so it's going to be 4. And then -4 plus 1, so that'll be -3. Okay, so 4, -3. Okay. So it can kind of be hard to get a feel for like what the exact graph of these are, unless we start graphing like a lot of points. Let me see if I can do this on the graphing calculator online and show it. Okay, so going into Desmos online here, so it looks like it's fairly straightforward. Let's see. So we have 3 t squared, or sorry, t squared minus 3t, it should have been. And I don't know if it's gonna like me using t. Might have to change that. No, it's fine. And then we can do this from like -100 to 100. Okay, so we can kind of see what the graph looks like. And that was similar to how our points were shaping up. But notice what happens when you zoom out. It kind of starts to go back around. So one thing that gets a little bit weird about this is that we don't really have the same kind of vertical line test with these type of functions. This is considered a function still. So even though, and normally when we're just looking at the x and y coordinates, this would not be a function because it would not pass the vertical line test, but this doesn't have that same restriction. So the idea here is that this actually, if you think of t as the time coordinate, this actually has a direction to it. So it starts like wherever you start your time. Say maybe you started at 0, for example. You would start right here, and then it would it has a direction where it moves this way and then keeps going in this direction here. Okay. So there's no 2 points at any one time is kind of the idea here. And it's hard to see that on just looking at the graph. You really need to see that just by plotting points yourself manually. Okay. So it's pretty different from normal graphs that we're used to. So we're not going to be so concerned with actually making the graphs because, they can be pretty challenging to do by hand, depending on the graph. Some of them, if they're smaller, they're not as bad. But it's good just to have kind of a basic understanding of what these look like. So the main point here is that they have a direction to them, which is that, we typically take time to go, forward, right, from 0 to 1 to 2, etc. So it would start like right here if you started at 0, and you could start it in negative numbers. You could have this concept of negative time. But then anyway, so then you would go forward. So it has this direction to it. Okay. All right. So I'll just go ahead and connect these, I guess, because so we weren't really going to see that it was going to come back on itself like this. But when you draw it, you might draw some arrows to represent the direction here. Okay. So this is getting a bit ahead of ourselves, but just kind of to give an idea of where we might see something like this. The main thing that you would see this in is in something called the gradient, where each component is a different partial derivative. So of course we need to talk about partial derivatives first, but you can take, when you have 2 independent variables on your function, you can have a derivative with respect to each of them called the partial derivative. So you might be able to make a vector function out of a vector of the partial derivatives, and that's what we call the gradient. And when you can even do it with a matrix of them, and we call that the Jacobian. So those come up somewhat in statistics, really more if you're doing like multivariate statistics. But so just something we want to introduce, but we're not going to focus too much on the graphs, like I said.